TAs led the discussion, and my understanding is we carry out quiz number 1, and they also went over how well you did for quiz 1. So how many of you feel that you did okay in quiz 1? Yeah. Like you sure your solutions are right, and I mean the TA did go over the solution, right? Of course, relational algebra and SQL, sometimes they are tricky. Your solution might look different from the posted solution and can still be right. But I hope at least you are able to judge whether your solutions are right or not. The TAs went over it, right? So how many of you feel that you did okay in quiz 1? Let me ask the question again. Only 1, 2, 3? Only 3? So the rest of you feel you did excellent or you did really bad? Alright, so we're gonna have midterm. Most likely I will schedule the midterm right before the spring break. So the Tuesday or Thursday right before spring break. Oh, sorry, fall break. Fall break. Yes. And then I will be able to do the grading of your midterm during the fall break and hand it back to you when you come back from fall break, right? So which means we have about, what, 2-3 weeks leading to the midterm. And what the midterm gonna cover is obviously homework 1 and 2 plus homework 3 that's gonna come out once we finish the discussion today, and hopefully by Tuesday lecture I cover all the things needed for homework number 3. So the midterm will cover at least these 3 homeworks, if not more, and depending on the progress whether we can make to homework 4 or not, but most likely not, right? So you definitely want to get ready for the midterm. So if you feel you are having trouble to do quiz number 1, either you don't know how to solve those problems or you cannot solve those problems in the time that's given, which is 30 minutes, right? Then you definitely need to do more exercise in order to prepare for the midterm. If you look at the problem in quiz number 1, I can say for a certainty that those problems are not the hardest ones you have seen from your homeworks, right? It's probably the average level in terms of how difficult they are compared to the problem you have seen in your homework, right? That will be the tone for the midterm as well. Most of the problems, but most, I mean more than 80% of the problems, will be similar to, I mean the level of difficulty you should expect will be similar to what you have seen in quiz 1. Which means if you are able to do most of the homework problem on your own, you should score at least 80 points or more in your midterm. Of course, we will have about 10 points or 15 points that's more challenging towards the more challenging ones you have seen in your homework. But those are kind of like a minority set of questions, right? Even if you are not able to solve them, you still score a big part of all the points anyway, right? But if you are not able to solve those even in the quiz number 1, then you definitely will be in trouble if coming to the midterm test, right? Of course, one thing that's different is quiz 1 is closed book, and midterm will be open book. So that will definitely help. But in my opinion, it helps only a little bit, because this is not a history class where you memorize what happened on which year, who did what. The open book definitely helps a lot in those cases. In this case, even if it's open book, it doesn't really help, in my opinion, right? It doesn't really help that much. Yeah.
I'm sorry. What did you say the scope was of the test? Was it just relational algebra and?
For the midterm will be definitely relational algebra and SQL, as well as homework number 3, which I haven't released yet. But I'm hoping to release that either today or by Tuesday's lecture, depending on the progress we can make. Okay. So those will be in the midterm test. And so that's all I want to say for quiz and midterm. We will have another quiz, of course, before the midterm. That's to test the content covered by homework number 3. So you will have sufficient resources to do exercise for and to test yourself for. So how quiz 1 give you kind of a way to gauge where you are. Right? If you do pretty well in quiz 1, then you should feel fairly confident in midterm. You are looking at least 80 points, maybe even 90 points from midterm if you are able to do quiz 1 in the time that's given. Right? Otherwise, you want to exercise a little bit more, right? To sharpen your skills a little bit better. That said, now let's move attention to the project, right? Project 1 has been out, which was supposed to be due today, but because I was out of town Tuesday, I missed the office hour. I do want to give you a chance to talk to me if you have doubts. So I have extended the deadline for Project 1 to this Sunday. At noon, right? At noon. So if you still have any questions regarding Project 1, you should definitely talk to me or the TA. Either come to our office hours or send emails. My understanding is by talking with many of you, my feeling is most of you have done pretty okay on Project 1. Which is not that surprising because Project 1 is rather straightforward. If you followed what I have said in lecture, explaining this page structure is exactly the same, except that we reverse the order of slot entry and data space, record space, that's all. So in the lecture slide, record grows forward and slot entry grows backwards, starting from the end of page and starting from the beginning of page respectively. In the project, it's exactly the opposite. The record grows backward at the end of the page, and slot entry and some other metadata information about the page are placed at the beginning of the page and grow forward. That's probably the only difference I can tell from UE implementation and what we have said in class. Okay? So taking this as a good opportunity to ask any questions, any doubts or concerns or questions you may have on Project 1, you may ask now. But don't feel embarrassed asking a question, right? So this is a really good time to ask. Maybe the doubt you have is shared by many others in the class, right? So this is a really good time to ask them. Yeah.
The page length, when we are considering the records will be inserted from the end of the page, is the page length will be considered as the number of bytes we can store in that, which has been given by the db fixed sum?
I think you're asking two things. One is, when record is inserted, yes, they are inserted backward, starting from end of page. Of course, that's end of page, starting from end of page only happens for the first record to be inserted. The subsequent record insertion will start from the use pointer address, the end of the record space.
My main question is when we are maintaining data array, the index which we are assigning.
The index which we are assigning, okay.
Yeah, that is the address of the byte over there when we are considering page.
I don't think I quite understand your question. So the index we are maintaining for the record is the slot entry.
Only for data array. Slot has the byte information that at which point it will point. The offset first time when we are inserting a record, suppose I am inserting first time in a new page. So
well, if you first time insert to a new page, that's what I said just now. You start from the end of the page. So this is our page structure, right? There's some metadata information here, such as previous page ID, next page ID, current page ID, and a bunch of other things I don't remember on top of my head. But here we go here. Okay? And then the header file has declared a data array, which is the page length minus the size of metadata. Right?
My question is this page length.
Sorry?
We didn't given any page length variable.
The name of the variable might be different. It might not be page length, or it's something else. It's something that denotes the page length. Okay? And which means the length of data array is from here all the way to the end of the page. Do you follow me? Do all of you follow me? And that's simply a byte array. That simply is a byte array. Because this is declared as, if you trace the code, it's a character array, but character array is the same as byte array. One character is exactly 1 byte. So this is a byte array. And page length, this is a constant that's not defined this particular header page, but it's defined in, I think, in db.h. If you do a graph of this variable here, from all the h file, you will find where it was defined. Okay, I believe the default value is 1 kilobytes page. Okay, if you just do a graph, you will find where it's defined. Do you follow me, all of you? And then here comes, yes?
Is there also a function that we could use to calculate the page length?
You can calculate it. Well, no, page length is given as a constant, right? You cannot calculate this per se. You see what I'm saying? It's called dp fixed, right? Is that the name of the variable?
Maybe it's like mini page.
I can look it up.
It's in mini-rel.h, it's in page.h and then not refers to a macro.
Let me look this up. So dp fixed is the dp fixed is the size of the metadata of the page. Okay? And data is max space minus dp fixed. Okay, the max space is what I mean here by page length. If you just do a graph, max space, not max space. You see where it is defined. It's defined as page.h, which is defined as mini-base page size, and you can further trace that by graph. And that's defined as 1 kilobyte. Okay? Do all of you follow me? And by the way, this is something that you all should know how to do. Of course, now you have no excuse of not knowing how to do this. But even before I do this demo, you guys should, if I were you, the first thing I would do is trace where this is defined and find where it is defined. If you're using IDE, some of the IDE are smart enough to link this automatically for you. If you mouse over, it will show you the trace where it is. But even without IDE, this simple couple graph, you will find where it is. Okay? Any question on this? No? Okay.
You delete a record, how do you move?
Okay, that's jumping forward. Let me, but deletion I went over in detail last lecture, right? So you should at least review the YouTube video if you haven't done that. Okay.
In the sample output,
Louder, can you speak louder? Yes.
in the sample output which you have given in the project, it says the relative space is 1000 and the free space is 1004. So I was a bit confused about that.
Let me get at you again. You are jumping forward. Let me try to answer her question first, which is how this size is calculated. Okay. So this is simply the dp fixed. Why is that? Because if you look at this definition, this dp fixed is one slot entry size, 4 short, and 3 page ID. That's precisely the total size of all the member variables of this class. Right? You know C++, if you declare an object of this class, it will allocate space for all the member variables. And the member variable of this class is what? 4 short, 3 page ID, plus 1 slot, which is here. Right? So the dp fixed is essentially the size of all these guys. That's essentially my metadata I have set up. Do you follow me? Yes or no? All of you, right? And again, if you know a little bit about object in C++, the sequence this member variable appear will strictly follow the order you declare them. Right? Which means you're going to have 4 shorts, 3 page ID, and then this is where your slot array starts. And another thing you should know, which is a very rudimentary knowledge about C++ and C, is that the array name is a pointer to the starting address of the array itself. So slot is essentially the pointer to the starting address of the slot entry. And we have declared one size 1 array, which means I have one element allocated already. That's essentially this guy here, which is my slot 0. You follow me? Where is data? Again, data is a character array, which means it's simply a byte array of how many bytes? Now you know, page set minus these guys, which means from here to here, that is 1 kilobytes. And I take away this many bytes, whatever that byte is, I don't care. And my data start from here. Again, data is a pointer to the starting address of this data array. Do you follow me? Yes or no? Yes. Okay. That being said, all you do is you allocate record backwards and you roll slot entry forward. Some of you ask me, okay, how do I grow this slot entry? Well, you do not have to allocate space dynamically since the starting address of the slot is here. So if you simply do slot 1, what happens? If you try to use slot 1, what happens? It will automatically eat into the space of the data array and it will allocate slot 1 right here. And of course, the length of this is the size of one slot entry, which is this struct I defined on the top, which means the size of one slot entry is the size of 2 shorts. That's it. So if you just use slot 0, slot 1, slot 2, slot 3, it will automatically grow into the data space. Because the way you have arranged these member variables at the declaration of your object. Do you follow me? I think with that, this project is rather straightforward. Once you understand these member variables and what they are, how they are placed, implementing itself should be done in, once you understand all of this, implementing this probably take you, I think at most a day, right? At most a day. For proficient programmers, if you're really good at C or C++, you should be able to do this in a few hours, I think, implementing all the functions, right? But if you're, you haven't done C or C++ for some time and you're new to this, probably take you a day once you understand. Because the rest is, you think about it really straightforward, right? You insert record, you allocate, you use one of the slots, right? Now, to the deletion question, if you delete one, you move all the record backward and update the slot entry accordingly. Of course, only update those slot entries whose offset is bigger or smaller than the offset of the record being deleted. Bigger or smaller depending on how you maintain the offset with respect to the idle page or beginning page, which I said in detail in last lecture. Right? So I'm not going to review the deletion procedure for you all over again, right? But that's just a quick recap of what we said. Okay. Yeah?
In get record, it is mentioned that we can get record as whatever you. So let's suppose I'm considering when returning a record from the one which I have inserted at the end.
Well, I think get record, the order of which record to be returned is defined in the documentation. Why not you just look at the spec? It's clearly defined. What do you mean by get next record? It clearly defines. Okay, I think I have to take question offline because I don't want to use too much time in lecture time to answer all the project related questions. But I think with this being said, you should be able to implement this fairly straightforward, right? In a fairly straightforward manner. One thing I do like to remind you, which I said a couple of times already, it's better to submit a half-cooked product or even an empty code than copying from somebody else. Somebody else is a big scope, either someone from this class or from the internet, or somehow you get the code from previous batch. I have a repository of all the submissions since I joined Utah in 2011, so I have 4 years or 5 years of repository with me. So I'm trying to be nice here, right? Because I tell you what I have. Because I can do a game where I didn't tell you I have all the 4 years of repository and you try to copy, you think you can escape from that. But no, you will not be able to, all right? So just a warning ahead. I'm much willing to give you some partial credit. If you submit a partially done product, you will get partial credit as much as you deserve. Then try to copy from someone else. If you copying from someone else, I mentioned that at the beginning of the semester, the policy is the school community has 2-strike policy, right? If you copy twice, you will be expelled from the program altogether. If you copy once in my class, I will not fail you from the class immediately, but I will fail you for the product, which means you get 0 for the product. Not only for that product you copy, but for the entire product. Okay? Am I clear? So if you call cheating, for example, for product 1, you got 0 for product 1 and all remaining product, which means you don't have to bother doing the remaining ones. Okay? I don't know if that's good news or bad news. But you know, if you do a partial implementation, trust me, right? We will give you credit, right? So definitely go with that rather than try to copy from someone, right? So there's no point of trying to copy because the whole point of a product is to give you a way to learn, right? If you copy, then what's the point? You get 100 and you learn nothing at the end of the day. And you may be able to get away from this class, but when you go for interview, you will not be able to get away. And even if you get away from interview, you join the workforce, and if you're not able to do the task assigned to you, what's the point? Right? So in the long run, you suffer. Right? So there's really no point of doing that. So I'm very strict on this as well, and I tell you we use a particular way to detect copying and plagiarism, simply changing variable name, swapping function around. All of those will not work because we look at the binary output from the compiler. So if you do copy code, very likely compiler will do optimization such that 2 codes that are original from the same source will end up in very similar binary code. So I just want to emphasize that one more time, right, before you do the first submission on Sunday, right? Let's hope we do not have any case. I hate dealing with this case like this. It's always an awkward situation for me and for the student involved, right? So let's rather not to go down that path at all, right? Let's try not to go down that path at all, okay? All right. That said, let's move on to lecture, okay? Oh, by the way, for those of you, many of you have already finished project 1, right? So rather than keep you waiting in the queue, I move ahead and release project number 2. So project number 2 is on buffer management. So the remaining semester will be somewhat similar to this. So you will be done with one project, and at the due date of the previous project, the next project will be released, right? So it's like build upon each other. And project 2 is buffer buffer manager. So essentially, you will implement what we said in class, but with a particular buffer replacement policy called love or hate. So you either love a set of pages or you hate a set of pages. Of course, there are another set of pages you do not love. You basically feel indifferently about these pages, right? So a love page means that it has a higher priority to be staying in the queue. A hate page has the lowest priority in terms of trying to stay in the buffer, and in other words, it has the highest priority to be kicked out from the buffer. That's essentially the love and hate policy. This gave some power to the application program to specify how they want to try to keep pages in the buffer. So application can predict what pages might be accessed in the future and what pages might not be accessed in the future. And the one you predict that with high likelihood to be accessed in the future will be your love page. Otherwise, it will be your hate page, right? And the ones that you have no prediction whatsoever will be those ones you feel indifferently about. Make sense? So that's the love and hate policy you're going to implement. And in implementing this, you will need to have a hash table. I do not allow you to use the hash table provided by STL from C++. Rather, you will implement your own simple hash table. But hash table is fairly easy to implement anyway, so that's just give you a way to practice how to implement a hash table, right? So you will implement the hash table yourself and use the hash table structure to implement the love and hate policy and the rest of the buffer manager functionalities. Okay? And one thing I'd like to mention is that's why you notice in product 1 release we have a file called the .o file for the buffer manager. That's essentially compiled from my implementation of buffer manager. Of course, I cannot give you buffer.c because that's essentially what you need to implement on product 2. But I still want you to be able to implement your product 1. That's why I have to give you something that's linkable. So I give you the .o file, not the source file. So similarly, on product 2's release, you will find a file called page.o, which is compiled from my implementation of your product 1, essentially. Of course, I didn't release the source code of this because otherwise some of you are still working on your product 1, right? So I give you the .o file, and fortunately we can do this with C and C++ because reverse engineering C code is hard. Unlike a Java code, if I give you a .class file, you can very easily to get the .java file back, right? So, but .o file is not easy to be reversed to get the source code. Okay. So that said, if you are fairly confident in your implementation of product 1, so when you come to product 2, instead of using my .o file for this, you can use your .c file for each page implementation. If you are confident in your implementation, of course, you run the risk of having some bugs that are not detectable by our test cases and then surface in your implementation buffer manager. That makes you debugging a little bit trickier on product 2 because you don't know whether it's because you implemented your buffer manager or because of the implementation of the page itself. Do you follow me? But if you're fairly confident in your implementation, go ahead with that. And then if you're fairly confident in your implementation of product 2, then when we come to product 3, you can use your implementation of product 1 and 2 for that. Okay, yes?
So if we do decide to use our own, should we keep everything that's in the make file, like just keep it as it is and then maybe add our own elements?
Well, for the most part, I think for most of you, you do not want to modify the make file, and I don't see the need of doing that as well. But for some reason, if you want to add an additional .c file for additional add an additional class that needs to modify the make file, yes, go ahead and do that. But I can tell you that for all the product we hand out, you do not need to modify the make file in order to get it work. But that doesn't mean you cannot modify the make file. Right? That just means there is the path available to the solution without making any change to the make file. Okay. Any other questions? Okay. So this product is due Tuesday. Tuesday, 2 weeks from now. Not next Tuesday, the Tuesday after next Tuesday. Okay? Which means if you finish your product 1 on Sunday, you have about 9 or 10 days to implement product 2. Product 2 is definitely much harder than product 1. So if you spend just a day on product 1, you should plan to spend at least 2 days on product 2, or even more than that. So get started early, right? That's my advice for product 2. Okay? So I just want to do a quick run through of one example that I didn't have time to go to regarding this page optimization. So suppose this is my initial setup page, okay? So 35, 4, 30, 10, so on and so forth, right? What this means offset is 0 and length is 10. So obviously I'm calculating my offset from the beginning of the page. Okay? So that means the first record, the record ID of that page is I4 because it's page I, and the fourth slot entry. So that's I4. You follow me? Of course, depending on how you index the slot entry, it could be I3 if you start from 0, right? But here I start with 1, so it's 1, 2, 3, 4, it's I4. Okay? And the second record in the record space is actually my I2, because it's the second, it occupies the second slot entry with the length of 10, with the offset of 10 and length of 8. Why offset is 10? Because the length of the first record is 10. And start from byte 0, go all the way to the byte 9. So the starting address of the second record is at offset 10, starting at byte 10. You follow me? What about the third record? Well, the offset of that will be 18, obviously. The sum of the length of the first two records. With the length of 12, so it's I3 because it occupies the third slot entry. So the offset for the last record in the record space will be 30, the offset plus its length. And since the length of this is 5, so my use pointer, or the starting of my free space is 35, offset 35. And I have 4 slot entries, that's why my n is 4. Okay, so that's my reading of the initial state of this page. Any questions on this? Now let's try to do some deletion and insertion, see how it goes. Let's go with deletion first. So I try to delete record I2. If you try to delete record I2, this is the record to be deleted, right? Do you follow me? So the first thing you will do is to move all the subsequent records forward by the length of the deleted record. In this case, I will move I3 and I1 forward by how many bytes? By 8 bytes. Precisely the length of the record to be deleted. Okay? And after that, I need to update the slot entries for record 1 and record 3. Why? Because these two are the records being affected. I do not need to do anything for record 4 because it comes before the record to be deleted. Henceforth, it's not affected at all by this deletion operation. So how do I figure out the slot entries that correspond to these two records that are being affected? Well, with the way I calculate my offset, it's very easy to figure them out. The slot entries whose offset value is bigger than or larger than the offset of the record being deleted will be the record that will be affected. Because they come after, they indicate that these records they actually come after the record that is deleted. So you do a linear scan of your slot entry, the offset of record being deleted is 10, so whoever's offset value larger than this will be affected, which means you identify these two, but this is not. And once you identify this, you adjust the offset value by how much? By the length of the record being deleted. And in this case, you minus away that length because you calculate offset from the beginning of the page. So this becomes what? 22, and this becomes what? 10. And this will be affected as well because that's the starting of the free space will be decremented by 8 as well. So what you get? You get this. You get this. You got 10, 22. The length stays the same. And this is 27. Notice that this is still 4 instead of 3, as I said, unless it's a deletion of that corresponds to the last slot entry. We never deallocate a slot entry for a deletion. because we are hoping that we can recycle this slot entry for subsequent insertions if it's something in the middle of the slot entry. So we do not try to dynamically compact the the slot entry space. Rather, we simply mark this as -1, -1 to indicate that this slot entry used to correspond to a record but now has been deleted. Do you follow me? That's why this stays as 4 instead of 3. You do not decrement this to 3. Still is 4. Yeah?
I was just going to mention in the project, in order to pass all the tests, you have to end up deallocating the slots.
You have to?
Yeah.
I'm not sure about that. So
it checks like the free space before and after, and if you don't reclaim the slots.
Well, depending on how you maintain the free space, you can maintain your free space in a way that you count for this slot entry size, even though you haven't deallocated yet, but you just count it as part of your free space. You know what I'm saying?
Yeah, that's true.
You get what I'm saying, right? Okay. Of course, you can, deallocate this, but you don't have to do that. Rather, you just maintain a quote-unquote fixed free space that counts for the
you
slot.
have to be careful that it's like...
Yeah, you have to be careful with it. But that said, either implementation is fine. I don't really care which implementation you have to do that. But without compacting this, will give you a little bit of efficiency if you have a mixture of insertion and deletions. Now, let's go to insertion. If I do an insertion now, I will scan the slot entries one by one and identify any slot entry that is recyclable or not. If I do find a recyclable slot entry, I will use that. Of course, my record always go to the end of the record space and starting in the free space, which is 27 in this case. So it goes to offset value 27. Copy the content of the record to that space, starting from the offset value with the length of the record. And then you recycle this slot entry. The offset will be 27, obviously, and the length will be 5. So in this case, I do not need to increment my slot entry array. But if you do yet another insertion after this, you will have to allocate a new slot entry and increment the count from 4 to 5. Okay? That's it. Okay, let's move on to the new lecture. So before discussing this new lecture, I want to emphasize that the structure and the mechanism we have discussed so far, you will find that in classical relational database systems, which is called a row-oriented engine, right? Or store. A row-oriented store. Why? Because each record is placed into a page as a whole with all its attribute values. Okay? And record is placed after another. So one record after another, one record after another. And each record contains all the attribute values it has. So that's what we call a row store. Increasingly, there's another popular structure. It's called column store or column engine, which was proposed not a long time ago, proposed back in 2006, 2007. There's a classic work called C-Store. Again, this is done by a group of people led by this Turing Award winner this year, Michael Stuhnbaker. So he led a group of people from MIT and Brown and I think involving Berkeley as well. They proposed this concept and developed a system called C-Store back in 2007. And it went into a startup called Vertica. And this startup was pretty successful, was bought by HP. Later on. Of course, HP itself now is not doing so well, right? But Vertica, as a separate story, is doing okay. At least at the time being purchased by HP. After that, I'm not sure. Right? This purchase, by this big company, I'm not sure. Right? But leading to the purchase by HP, Vertica was doing pretty good. So column store and column engine, the major difference, as you can tell, is that inside the engine, inside each page, you do not store record row by row. Rather, you break a record into what we call column families. And then you store record kind of like vertically. You store all the columns, all the value from the first 2 columns first, for example, followed by all the value from the next 3 columns, and so on and so forth. These 2 and 3 columns are what we call column group or column family. And the reason why you want to do this, if you think about it, it's a very intuitive observation. In SQL and in relational algebra, we often do projection. And in order to support that projection, what you have to do with the row store is you have to scan all the records and then only keep a subset of the from each record, a subset of values you have to look at. And that generates a lot of unnecessary IOs from the bytes point of view, right? Unnecessary bytes reading from the disk. So if you have a really long record, which is increasingly the case, because for every object we try to model in a database, we try to remember everything about the object. It used to be we do normalization, we do schema refinement, we keep only the data relevant for your current application in the database, but increasingly companies ignore privacy and all that, rather they want to learn everything about you. Even as a University of Utah student, they may want to know what kind of computer game you like, which has nothing to do with the university, but I'm not saying University of Utah is doing this, right? Don't take me wrong, but just for the argument's sake, they may keep the information like this, and just for whatever needs down the road, right? They cannot predict at the moment, which means each record is getting increasingly long, right? If you do a row store to read the first name and last name, which may be only 20 bytes, you need to read in 200 bytes and throw away another 180 bytes and keep only those 20 bytes. But if you do a column store approach, you analyze your workload, you know most often you read only those 20 bytes, and you read them together. So you put them into a column family, and you store them together across different rows. That will be really efficient. And furthermore, added benefit of doing that is compression. You can compress these values much better now. Why? Because you have coherent values that are next to each other. First name, last name of the first student. First name, last name of the second student, so on and so forth. These are all string values. They are homogeneous. They are similar. So compression works much better. Compared to a row store where you have first name, last name, string values, age, integer, GPA, float, date, a birth, date in date format, and you try to compress a bunch of these guys, your compression ratio will be much worse because they are heterogeneous values. Okay?
What kind of storage do NoSQL databases use? Is it like at the bottom, does it just reduce down to row storage?
That's a very good question. So NoSQL is something we're going to discuss as well if we have time. That's why we need to make faster progress now if we want to get into all these topics. But a lot of NoSQL, NoSQL database, if you look at their engine, some of them use column store, some of them use row store. A popular NoSQL database, HBase, for example, they use column store. So a lot of key value stores, they actually use column store. But not always, not always. If you look at Spark, which is not a database per se, but it's a parallel analytical engine, in their storage, they use row store. But once you read data into the in-memory format, the engine by default goes with C-store, column store. So data is stored as row store, but when you read them in and try to start processing them, it will convert that to a column store for processing needs. So there are a lot of interesting things to be done here. Okay. You may wonder why compression matters. Oh, you can compress better. So what? You can save. So instead of 1 gigabyte on this, you use 500 megabytes. Well, storage is one part of storage. The biggest winner is I/O, right? Instead of reading 1 gig, now you read only 500 megabytes. If you can do compression better, right? So I/O is a big saving, not necessarily just the storage you're looking at. Okay. But in order to understand all of this, we need to understand the basics, which is come back to the relational database, and we will continue our discussion on relational database kernel. Right? Then we will move on to those more exciting and more recent developments. Okay. So next slide, next chapter is on file organization and indexing. So we talk about all these guys. Now we're pretty good at this, and we talk about files, and we fully understand what is a heap file by now. Right? Heap file is essentially, if you think about what we said, collection of pages. There are two ways of organizing these pages. One is to use two linked lists. One is to use one without linked lists, but a directory entries, one directory entry per page, and keep them in a directory, a collection of directory pages. And then within each page is a collection of records, depending on whether fixed length or variable length. You have different organizations, and within each record, again, depending on whether it's fixed length record or variable length record, we have different organizations. So go all the way from file to page to record to attribute value within record. We understand all of this inside out by now, right? Now all the discussion we have so far makes this assumption that records are not sorted within a page, right? So that's why we call them heap file. Another way to organize the record is called sorted files. So I want to maintain some sort of order when I place my record back to disk. Why you want to do this? Well, to make the retrieval of the record much faster, especially if you try to retrieve this record based on a condition that involves the sorting order you have in your file. Then you can do pretty much like a binary search over your file and quickly locate the record you are looking for. Okay? And then there are a bunch of other things, organizations of files, which is cluster file and unclustered file. Those we will discuss them once we have a discussion on index first. So we will defer the introduction of this later on. So we're going to introduce a cost model to analyze the benefit and the cost associated with each way of organizing your data. And the cost model is as follows. We use B, R, and D. This D, for the most part, this D, I only use this D because it was used in the textbook. So so in our discussion, most often the case we ignore this D factor, which is simply to annotate the time it takes to write or read a page. Okay? For the most part, we concentrate on how many IOs you need to do, input and output. In other words, how many pages you need to read from disk and write to the disk. And if you want to transfer that into a time, you use that number times D. That gives you the total time that will take. Right? But for the most part, we concentrate on analyzing the number of IOs, number of pages operation you need to do, okay? Which involve pretty much only B and R. Okay? Furthermore, we make some assumptions. Here we ignore things like prefetching, right? OS and also the database management system itself will do prefetching on a regular basis, which means if I observe that you are reading the first 1,000 pages from this file, most likely you will continue that fashion and read the subsequent pages from this file. So even if I haven't received a request from you for the subsequent pages, I'm going to prefetch those pages for you anyway. Why? Because now you know the disk structure, you know why. Because by the time you have read the first 1,000 pages, this arm head is located at the 1001 page. If you don't read this page, you miss the opportunity, right? It will be rotated by, and some other request may come in and move your arm away. So if you later on come back and say, okay, I'm done with the first 1,000 pages, give me the next 1,000 pages. What you have to do is pay random IOs again, like move your arm and so on and so forth. If you predict that the application gonna need the next 1,000 pages anyway, since you are here anyway, so why not take the opportunity and read them while it's being rotated by? So that's what we call prefetching. OS and DBMS, both of them do prefetching to some degree. And you can adjust the degree of prefetching you do in OS kernel. It's something inside the kernel, which means it's not so easy to adjust, right? Because if you just have one single value, you need to recompile the kernel. But it's doable. you can adjust the prefetching degree in OS, which means how aggressively should I do prefetching? Should I prefetch 1,000 pages at a time, or should I prefetch 10,000 pages at a time? Things like that. Okay. And furthermore, for the most part, we do average case analysis based on several simplistic assumptions. I will make those assumptions clear when we come to the discussion. And when the context is clear, I will also give you the best case and worst case analysis, but not always. Okay. So some of the assumptions we make in the analysis, we assume that we are doing a single record insertion and deletion, which often is not the case in a database, because oftentimes in a database I do batch insertion and deletion to get a better amortized cost. Amortized cost means that the average over multiple operations. I'll give you a simple example. Suppose for some reason, carry this particular object take you 10 minutes, right? But carry all the other remaining objects take you only 1 minute each. So the amortized cost of carrying all these objects is the total time carrying all these objects divided by the number of objects. So in other words, the cost of this 10 minutes, this very expensive carry on this first object is distributed in some sense over to all the objects. So the amortized cost may be much smaller than your worst case cost per object. Okay? So that's why in database oftentimes they do batch insertion and deletion to get a much better amortized cost per record. But in our analysis, we'll assume that we're doing a single record insertion and deletion to just understand what's going on. Okay? We also assume that in selection, unless otherwise specified, for a equality selection, we'll assume that there's only a single matching record from the database. Of course, this is not going to be true all the time. For example, if you search for a student named Eric, you will find at least hundreds of Eric from University of Utah, right? But we assume that in this discussion, if you do a equality search, unless otherwise specified, we assume that there's only one single Eric will be returned. Okay? If you do an equality search with Eric, for example. Okay? And for heap file, we assume that insertion always append is just an append operation to the end of file. And this is fine because heap file maintains no order whatsoever. So appending a record to the end is totally fine. And sorted file, we assume that, this is an important assumption, we assume that you do compact the record space across different pages, not within just a single page, but across different pages in this sorted file. Which means not only records are sorted within this file, but there's no space left empty between any two pages. You follow me? Okay? This has implications to your insertion and deletion operations, as you can imagine, right? We will come to the details of that later on. And the selection is on the search key. The search key is basically the key you use to sort, you use to do the sorting. By the way, this key has nothing to do with the key of relational algebra. Relational model, right? It doesn't mean this must be a candidate or primary key. This simply means the attributes you use for sorting. That's what we call search key. Okay? All right. And our goal is to fill up this table right here. Fill up this table. For different organization of your file, I want to know what is the average cost of doing the following operation. What's the cost of scanning all records? What's the cost of doing equality search? What's the cost of doing range search? What's the cost of doing insertion and deletion? With respect to this different way of organizing your pages or your records. Okay? Let's start with some easy ones. Scanning all records. What's the cost for heap file and sorted file? Ignore the last column, right? Because we haven't talked about cluster file at all. So just focus on the first two. So let me start. Then I will ask you to fill the cell, right? So I will do the easy one, right? Let me do the easy one. So scan all records is simple, right? You need to read all pages. Doesn't matter how you organize these records, right? Whether they're sorted or not. Because my goal is to scan all records, you need to look at them all. So the total number of pages to be read, whether it's a heap file or sorted file, is B. And reading each page takes D times, so the total time is simply B times D. For both heap file and sorted file. Okay, that's fairly straightforward, right? Now let's look at equality search for heap file. Understand?
Wouldn't it also be approximately B times D?
Sorry?
Would it be B times
Always
D?
B times D. Okay. Are you talking about the best case, worst case, or the average case?
Worst case.
Worst case. And you explain your rationale a little bit.
Because since the record is unsorted, you might have to search every record to find a specific record.
Okay? Do all of you follow that? To be more precise, right? To be more precise. If you do equality search on heap file, the assumption we have made, remember the assumption we made earlier. We said equality search guaranteed to return a single matching record. With that knowledge in mind, what will be the worst case to do equality search on a heap file? Well, the record you are looking for happen to locate at the last page of your file. So you scan all the way to the last page. Until then, you find this matching record. So you pay B IOs, B pages. But that's the worst case. What's the best case? One. You are so lucky. You load the first page, bingo, the record is right there. And here comes that critical assumption. Because you know there is a single matching record, given this knowledge, you can terminate your search as long as you have found one matching record. If I don't tell you that, what happens? It's always B pages. The average case, the best case, the worst case, because you have to look at all of them to be sure that there are no more matching records. You follow me? Unless somehow you know the total number of matching records for your equality search, then you can stop as soon as you have found those many records. But in most cases, you do not know how many matching records you're going to have, so you have to go all the way to the end to make sure you do not miss anyone. So the best, but here with the assumption there is only one single matching record. The best case is 1, the worst case is B. What's the average case? Half. Right? The average case is obviously half. Okay, the average case is half. What about sorted file? Can someone help me out? What will be the cost of doing equality search, knowing that there is only one single matching record, and you are trying to search that record? Of course, on the search key, which means the records are sorted by the value you are trying to search for. Let me ask one, right? I heard log, I heard this on sounds right, but let's be precise. Right?
BR plus D.
BR
Plus D.
You are talking about sorted file.
Yeah.
Can you explain
So basically, since they're sorted, the entire file is sorted, you basically search for the first record, and in every page, if that first record happens to be greater or less than, depending on what you're searching for, if you find the relevant page, you will basically have to do a linear scan on that page.
Okay, so what you're saying, let me try to draw this off. I understand what you're saying. So you're saying we have total of B pages, right? And each page has R records on average. So I have R records here and on each page. What you're saying is you look at the first record of each page. Is that what you're saying?
Yeah.
But by doing that, it will cost you B pages. BIO,
Sorry, just
B
B plus D.
So it's B, but why can't R?
Yeah, just D plus D, my bad.
Huh?
Just D plus D.
Just B plus D, okay. First of all, by just looking at this, this formula, you know the unit doesn't match. The unit. Like $1 plus 1 kilogram. What do you get? right? It's the same thing, right? B is pages, D is time in seconds. So it's the same thing as $1 plus 1 kilogram equals what? Right? Am I right? Or it could be $2. Why? Because you argue, okay, this candy costs you $1 per 1 kilogram. Or it could be 10 kilograms. Why? Because $1 buy you 9 kilograms of something, totally 10 kilograms. So it doesn't make much sense, right? When you see D plus D. So right there, you know this is not going to be right. So if you want to be right, you can argue it's BD plus D. Now this makes sense. You have B pages, each page you pay a cost of B times. So total times BD plus another mysterious page cost in the end, so BD plus D. So that's one answer. But if you do this, you're simply doing a linear scan pretty much. You're not leveraging the fact that it's sorted, right?
Maybe log BR.
Log BR times D. Okay. Base of what?
Base of 2.
Base of 2. Okay. Close. Close, but not quite. Log BR times D. What you are saying is I do binary search on all the records. Right? On all the records. But you don't have to do binary search on all the records. You can do binary search only on all the pages. So what we will do is very simple. You start with the page in the middle, which is roughly B over 2. And you check against the value you're trying to search for. Suppose that value is K. You check the K against the first record and the last record in this page. Of course, the search key value from that record, which, for example, the name attribute from that record. If K is less than this value, you can ignore this guy. Only focus on the page to the left. If K is larger than the value of the last record, what happens? You throw away all these pages and focus on these pages. When you focus on these pages, what do? You do recursion. You find the middle page of the remaining ones, which means roughly B over 4, and you recurse. And when does recursion terminate? Well, if you're lucky enough, if your K is in the middle of these two values, you know what? The record must be in the current page. In the worst case, how many pages you, on average, if the cost of binary search is pretty much just log, right? Why? Because each time you throw away half pages. By log 2b times, you have nothing to throw away. You have to terminate. Right? So essentially, this, if you look at this series, right? B half, B over 4, how long can this pattern continue? That's essentially the question, right? The pattern can continue for this many times. And each round, you load one page. You look at only one page, which is the middle page of the remaining pages. So each iteration, you pay one I/O only. So the total cost is simply this. Again, here we assume that there is only one single matching record. If you have multiple matching records, what happens? We will come back to that. Well, let's talk about that right now. What happens if you have multiple matching records? If you do have multiple matching records, you're dealing with the sorted file. So you know that this record must be consecutive with each other if you do have multiple matching records. So once you find the first one, you do linear scan. The cost of that will be log 2b plus number of, I call that matching pages. Number of matching pages. How many matching pages you have depending on how many matching records you have. If you know the number of matching records, how do you calculate the number of matching pages? Well, you use number of matching records times the record size divided by page size. That gives you a bound on the number of matching pages. And you can do linear scan because they must be next to each other by the fact that they're sorted. What about range search? What about range search? Well, Daniel.
So how come we don't have a factor of R included in the above equation since we're looking through the records?
Well, because each time you load a page, whether you, how many records you have in your page is irrelevant if you think about it. You're doing binary search on pages. You're not doing binary search on records.
But like if multi-search, are we searching for a specific record or just?
We are searching for a particular record, but we are looking at the I/O cost. We are not counting the CPU cost.
I see.
Make sense?
Yeah.
That makes sense to you, right? Why? Because if you look at the I/O cost of reading a page compared to the CPU cost of cycling through the record in a page, the second is minor. And in fact, once you load the page in, you compare the first record and the last record in the page, the value, search key value of those against the search value. If they're in between, you know this record is in this page, but you still need to find this record on this page, right? Here you can do a min-memory binary search on this record. That's a cost of log 2 of R, but you don't have D, because D is the time reading a page. There's no I/O involved here when you do this log 2R search. And this value is much, much smaller than this. Because this is log 2R CPU or CPU comparison operation, which is nanoseconds. And these are in milliseconds, 1,000 times difference. So you ignore that. But even that said, you are doing a log 2R search, not log 2 of B times R. Because if you are doing log 2 BR, what you are doing is, if you write like this, what happens is you make one assumption, which is memory is big enough to hold all the records. And you load all the records in the first step, you linear scan all the records into memory. Then you do a binary search over records. If you do that, the total cost is what? B times D plus log 2BR. Suppose this D matches the number of CPU cycles, equivalent number of CPU cycles of reading a page. That's you do that. You follow me? Of course, there's another assumption, which is memory is big enough to hold all the records. And this obviously is no match against this. And because this term alone is bigger than this, so you will never ever do this. You go with this one.
In sorted file, like each record will have many fields. So based on which field?
Search key field.
Search key.
Yes. Which is of your choice. You can denote whatever attribute you search.
So wouldn't it be log 2B times D over 2? Wouldn't that be the worst case?
That's a good question. So in sorted file, indeed, I mean you can argue that this is the. Let me write it down. So what Eric is saying is, isn't the average case this? Because the worst case, the best case is 1. The record you're searching for happens to be in the middle page. The first page you load in is bingo, you got it. Right? The worst case, you do the binary search all the way to the end, and you find the record in that page, or you find there's actually no matching record. But to get to that knowledge, you have to search through all the possible iterations, log 2B of that. So Aiden, the average case of this. Well, I think the answer is yes. The average case should be that, but if you compare these two values, log 2B and over 2 and 2, they are, symptomatically speaking, they are roughly the same. So, I mean, of course, you can make the same argument of that. Half B is same as B, right? So, okay, to be precise, you can divide 2 with this to get the average case. So that's a very big question. Okay. Next, range search. So let me go on with range search with you together. So range search cost for heap file is B times D. Why is that? This is because you don't know how many records you're going to have satisfying a range search. Example, give me all the students with GPA between 3 and 3.5. You don't know how many students are going to be in 3 and 3.5, and they are not sorted. So the only way you can do it is by scanning through all the records, which is B. And that's the best case, that's the worst case, that's your average case. You have to look at all the pages. Check each record to be sure that there are no more records within your range. You can only be sure of that after you have seen all records. So the cost is B times D.
So in a very, very best case, if we know that the range is the min and max value, couldn't that just be constant E for everything?
Well, then it's still B, right? It's still B. Return everything is still the B. So it doesn't matter what the assumption is, you have to look at all records. Solid ball, then this is similar to the argument I have just made for the number of matching pages, if you have more than one matching record. What you do is, you take the minimal value of your search range, for example 3.0 and 3.5, you take 3.0 as your search key value. And you search for the first record with that minimal value in your range. Suppose you find it using log2b IOs, binary search. Then you know for sure that the subsequent records that come in the range must be consecutive to each other and come right after the first record you have just located. Why? Because it's sorted. Of course, without saying, the range search is on your search key field that you use to sort your file. Otherwise, this is effectively a heap file. And you use log2b IOs to find the first record, then pay an additional matching number of pages IO to read all the matching record in your range. One question is, when do you know you can terminate? Well, you go until you find the first record that's outside the range, then you know you can terminate. Again, because it's sorted. What about insertion and deletion? Well, insertion for heap file is simple, right? We said it's always a append to the end. So the IO cost is 2, not 1. Why? Read page into buffer manager, update, make it dirty, and when it is replaced, write it back. So it's 2 IOs. What about sorted file? Well, this has to do with our assumption. Our assumption earlier is that this is compact. Otherwise, the cost might be different. But assuming that the record space are compacted, not only within a single page, but across different pages, what you do is, in order to do an insertion, you cannot append in the end because you have to maintain the sorted order. You use log2b IOs to find the place to insert this record. How do you do that? Well, you use the search key value of the record to be inserted to do an equality search. That ought to give you the place where this record should go into. But there will be no space for you to insert that record. We know that for sure because these guys are compacted. So what you have to do is move all the subsequent records forward by the length of this record. But this move operation goes beyond a single page. All the subsequent pages will be affected. On average, half of the pages will be affected. On average, I'm saying the average case. Which means you need to read half of pages in, update them, and write them back. Plus the binary search cost at the beginning. So the total cost is times 2. You follow me?
Can you put the lights?
Oh, yes. Oh, so let me know anytime during the lecture you have any questions or requests. As long as I can accommodate, I will do that. Okay. So this is for searching the place to place this record. Half B, because on average you need to move the records from half of the pages. Times 2, because you need to read them in, update, and write them back to make space for this record to be inserted. So the total cost is this. What about deletion? Is deletion still 2D for heap file? How many say yes? doesn't mean yes. Okay, I just saying you need to raise your hand. Okay. Well, no one says yes. Okay. Excellent. Yes is the wrong answer. Right? So what will be the right answer though? For deletion. Huh? Yeah.
Just like insertion to a solid file, so you have to delete the record and move the rest of the record back.
Oh, I'm talking about heap file, so you don't have to worry about moving stuff.
You have to find the record. So
You have to find the record. Excellent. Yes. So you pay the search cost plus. By the time you don't, okay, it's tempting to do search cost plus. Search cost is 0.5b on average plus 2 because you use read and write that page you find. However, it's only plus 1 instead of plus 2. The reason is by the end of your search, the page that's going to be affected is already in the buffer. You only need to update that in the buffer and write it back. So you only need to pay one more write. So it's search plus 1 instead of search plus 2. Because once, by the time you find it, it's in the buffer already. You don't have to pay that read cost to fetch the page. It's already been fetched. The fact that you found it means that it must be in the buffer in the first place. That's it. But for bandwidth, for sorted file, it's simple, right? It's search cost plus, again, on average, you affect half the pages. This time, instead of moving them backward, you move them forward, read and write. Okay? So that's that. Next, I'm going to talk about index. Is this good? By the way, again, don't try to memorize formulas. Because all of these numbers here, they are up there because of the assumption we have made. For example, this log 2b plus b is only here because we assume that solid files are compacted. If I don't give you that assumption, I said each page is about half utilized, 50% utilized. Which means 1 kilo page size, you only use on average 500 bytes. You always expect to find 500 bytes of free space. Then what's the insertion and deletion cost? That means that the insertion cost is log 2b plus 1, deletion cost is log 2b plus 1. Why? The search cost plus the one more write you need to do instead of plus b. So you always need to be careful in the assumption you have made, right? So memorizing formula is not going to help. And do not memorize formula. Do not memorize formula. Yes?
Why are we bothering to differentiate on constants in front of the...
Oh, that's a good question. If I use big O notation, then yes, it doesn't matter. For example, this 0.5b is gone, and so on and so forth, right? But here, I'm trying to be precise, just to make sure you follow the strict steps in understanding what's going on. But yes, Monty is absolutely right. If you go with big O notation, why you bother with the constant in front? Okay, I think we have enough set today, and I'll give you time off. Okay, I'm not gonna release. Okay, I'm gonna release homework 3 today, and you are not able to solve all the problem in it, but you can at least start working on it and solve some of it. But do start working on project 2 if you have already done your project 1.